Yeah. What is that for us? Nice.
Okay, good evening, everyone. Okay, not sure if any of you feel the same way, but it feels like November flew by, so we're already in December, the heart of the holiday season, but it's great to see a full room again, and happy holiday season to all. We are graced with the presence of St. Nicholas today, so him and Mrs. Claus will be taking pictures at the Christmas tree afterwards if anybody's interested, but we wanted to make sure he had a nice hot meal, so we didn't want to bother him too much. So, okay, so this will be our last in-person chapter event. There may be a virtual lunch and learn around the holiday period, and then January, the first Wednesday of the month, that we're contracted with restaurants, New Year's Day, so that's not a great time to have a project management meeting if you want anybody to show up. So we'll be back on the first Wednesday of February, but more on that in a minute. But just a chance to reflect on the year. For those of you who this isn't your first meeting, you know that our first meeting in February started with the news of the death of our active president at the time, Mr. Charlie Geis. So not a great way to start a program year for a professional association that's all volunteer, but credit to all the board members, credit to our chapter members. We were able to be resilient, held 15 events this year. We returned our 2-day member appreciation symposium for the first time since 2019. By a show of hands, who is there for that? Okay, you were there. We also had our member appreciation dinner last month. Many of you were here in this room, and one of our strategic goals is to break out of the monotony a little bit of just dinners the first Wednesday of every month. So we did have a project management night out at the ballpark, and are continuing to think outside the box more for 2025. Okay, so our next dinner meeting will be Wednesday, February 5th. Mr. Don Hoffman is the Director of Operations for the Sierra Nevada Corporation, one of the leading consultant firms in the great state of Maryland, and his subject will be what took me 30 years to learn about project management. So, and he still looks fairly young, so I think he'll have hopefully another 20 or 30 years. So we'll be opening registration there probably early January, but stay tuned for that. Keep tabs on our calendar. This is just a snapshot of our calendar for December. This is where you can find not only our chapter events, also the chapter events of our sister chapters, and then just industry webinars and different things that are free. So if you find yourself not that motivated to pay attention at work or with some free time, this may be good. But for every webinar invite that the board gets, we try to at least, most of them are free anyway, so try to put those events there. So stay tuned for that. Does anybody need a job or have a job? Bill, did you want to talk about the? No. Okay. Okay. Yep. And welcome Mr. Earl Taylor to the stage.
Thank you. My name's Earl Taylor, project manager. I currently work in customer success. So for those of you who aren't familiar with the function, it's post-implementation. I work for a software firm. Thank you. Post-implementation, taking care of the customers, making sure they continue to be successful with the product, adopt more. I also handle commercial, the renewals, upsells. So if someone has a role, I'm looking for a new position.
There's a hand up over here. Would you like to come up? Let's give her a round of applause.
Hi, good night, everyone. Hi, I'm Audrey, and I have been a project manager of PMP from 2010, and I work in various areas in project management, knowledge areas, IT, in helping strategic development, business development, and understanding of organizations and their development. I'm looking for a job in managing a project or two, or in an organization that is looking for someone who understands what the big picture is like. And I'm also a systems engineer, so I think like that. And I believe that in understanding project management and as a systems engineer, you have to think as a system because you have to consider all the different aspects to make sure that the project will be successful. So if there is anyone that knows of a position, because I recently got laid off, so I am looking for something anytime soon. So you can let me know. Thank you.
Thank you, Ms. Nelson-Simmons. Okay, if you need PDUs over the holiday season, we're one of the, I think there's 5 or 6 other chapters around the world that puts all their content on a YouTube channel available to everyone. And if it doesn't have a claim code associated with it, reach out to a board member and we'll fix that. So good background noise if you're working in a lot of subjects. Since the pandemic, I think all our recordings are up, or 95% since 2020. So a lot of good content. We're also one of the few chapters that have a Sisters Toastmasters group. We're lucky enough to have the president of the chapter here. Would you like to make an announcement? No? Okay. So they meet on the 2nd and 4th Wednesdays of the month, and the next meeting will be next Wednesday via Zoom. We can all be improve upon our public speaking. Your chapter president most of all. So if you're looking to challenge yourself in new ways with the new year, join a Toastmasters group, build a new network would be a great opportunity. Okay, former chapter board member and project management industry leader, Miss Laura Bernard, released her first book earlier this fall. So that's an Impact Engine. You can buy the Kindle copy or hard copy on Amazon. And speaking of books, we were lucky enough to have Dr. Todd Kashdan, professor of psychology and best-selling author, be our day one keynote speaker. And he was willing to waive his speaking fee for a book exchange. We had more no-shows than we thought, so we still have books. So everybody should have gotten a raffle ticket. So Santa Claus is waiting for the coffee, or we'd have him come up and give them out.
No.
Yeah, call him, or can I give him up? Okay, sure. And if you win, if you want to raise your hand or come up, that'd be great.
What do you want, the last four or the last?
Last three is good. 226. Hey, we got a winner. Yeah.
240.
I never win anything.
Yeah, you just did.
How many you want to do? 3?
Oh, this is no good. 245. 245. Somewhere I heard somebody scream. I'm trying to dig mine out here.
That would be a Christmas card.
I need that. $205. I think that's it.
Thank you.
Yeah, 205. 1, 2, 3, 4. One more. Oh, these are rigged. You know that. 231. Where? In the back, of course. And for those of you that want your picture with Santa, we'll be staying a little late.
A round of applause for Chris Kringle. Okay, in the spirit of the holidays, I'm not sure if they do it for us, but we do it for our sister chapters. So, I just put it over there. I'm sorry. Miracle on 34th Street approach to promote our sister chapters events. So PMI WDC, the largest chapter in terms of members in the country, has a bowling and ugly sweater Christmas party at Pinstripes in Georgetown on Saturday. So if you find yourself without any plans on Saturday, that would be good. And then next Wednesday, they have their monthly meeting. They have their meetings at the new Virginia Tech building in Ballston. So stay tuned for that. Baltimore's on winter break, and they're looking forward to coming with the new year with some great programs. And Silver Spring, just down 495, has their last meeting of the year, a virtual event on what's your PM brand. That's 2 Wednesdays from now and free. So great opportunities there. If your company had annual education and training allowances and there's 4 weeks left in the year and you have an opportunity to use it, our education partners are doing great things. If you're looking for an AI certification, we just had a lunch and learn a few weeks ago with one of our chapter members, and he stated a few entry-level AI certifications that would be good if you're looking to kind of pivot more into data science or machine learning or Gen AI. Okay, and it's our distinguished honor to welcome Mr. Ron Smith to our chapter stage for the first time. I'm not sure if it's a good thing or a bad thing, but we're also joined by Mrs. Smith. So either that's for support or to be heckled. We'll find out. Ron's a senior physicist at 4S Silver, one of our sponsors from the symposium. He received his bachelor's degree from MIT at a time when the education, not that the education standards aren't high now, but when they were maybe at their highest. He also was one of the first to develop the fiber coil wiring solution that resulted in over $1 million in business and revenue. And granted, Boeing's got a bad rap, but in 2005, they made a great decision to give him the prestigious Pride Award. And welcome, Mr. Smith. That'll be
Oh, that depends on the flag.
Yeah.
How about a green light?
There's a laser pointer up there.
All right.
Yeah.
Buttons for that.
Yeah. Other hand. Yeah.
Okay. Up the other way. Good. Got it. Okay. I heard that. We have a lot of MIT jokes around the 4S. Okay. First of all, I'd like to thank Matt. Okay. I'd like to thank Matt and Bill for inviting me to this venue. It's a nice opportunity to talk about technology that I love. And also, I'd like to thank my wife, who has been standing beside me. She's definitely the wind beneath my wings. So thank you. Before I start speaking, I'd like to ask by a show of hands, how many people here have some connection to artificial intelligence, be it as a user or developer, oh, I see a lot of hands. That's great. So this talk is intended for you folks. Now, sort of a different related question. How many here are actively working in the technology for artificial intelligence? There's a couple here and there. So we'll pitch the talk to where it probably will be of interest to everyone, but some of the points will be particularly noted by those who are in the technology. Okay. The thing to notice about this chart is that there is a patent pending. We applied for a patent on the technology, and that's a good thing because I can talk about everything that's in all of these slides, and it's all protected. I don't have to get non-disclosures from everybody in the audience. Okay. Outline of the talk, photonic interconnect technology snapshot, relevance for artificial intelligence, and the business development path. Okay. There's a lot of work ongoing right now in the development of computer chips that will support artificial intelligence systems. And this work has achieved remarkable progress. Present day state of the art is 64-bit words, 10 million cores, 10 million cores, 10 to the 18 floating point operations per second, exascale they call that. And so there's a lot of capability in the processors. Now, however, the emerging systems face certain limits. Among those are the power and thermal management, signal crosstalk, and importantly, interconnect density. You've got a lot of information generated in your processors, but you have to get it out to the rest of the world. And that is a bottleneck at the moment. So photonic interconnection is recognized as the best way forward. And there are many people working on photonic interconnection, optical interconnections. And 4S is among those. Oh, thank you. So I'll concentrate on the pointers. You got the slides. Okay, that's good. The title then of the technology is Massively Scalable WDM Wavelength Division Multiplexing Photonic Interconnects, a 4S emergent product. And just to begin to tell how this works, this slide is sort of an overview. Not shown is a frequency comb generator. There it is. That's directed through a grating spectrometer, which images individual comb wavelengths onto an array of modulators. And the modulated signals are multiplexed and routed to output optical fibers. And input signals are demultiplexed to a detector array. Next slide. Now we're going to drill down into that block diagram. So we started out with a lithium niobate frequency comb generator, and then we go into the spectrometer. So a grating spectrometer will accept parallel input from M optical fiber layers and image N wavelengths onto an M by N array of modulator waveguide. Yeah.
Might want to mention how much M stands for.
Well, M is the number of layers, and it could be 100. And having that question. Oh, by the way, I forgot to mention. Anybody who has a question as I'm talking, please raise your hand. In fact, you might have to shout. I spend a lot of time looking at the charts myself. So anyway, feel free to say what.
Reading down, it says M equals 100 is 160.
There you go. You have to, if you're patient enough, you can get the answer to your question.
Empty up the podium.
Oh, okay. So a Mach-Zehnder alternate optical frequency splitter, not shown, separates the dense original comb generation into 4 manageable wider frequency combs. So let's follow the light here. We start with our frequency comb generator. We go into a grating, and the grating spreads the different wavelengths that are in the comb out into individual spots. We have outages from time to time. Don't worry. And each of those wavelengths goes through into the internals of the chip and is modulated there, comes back out and is re-multiplexed through a spectrometer. And at that point, you've got a lot of information on this single fiber. You've got 25 gigabits per second on each wavelength, and you have 40 wavelengths on each fiber, and you've got 4 fibers with each of 100 layers, and 400 output fibers, and each one carries a terabit per second. So there's a lot of data flowing out of this chip, and put that into context. The people who make processor chips have been faced with a concern or problem with how do you get the information out. So the first line of defense in the old days was to just put more pins on your connector, your input-output connector. So I went to a trade show lately, and the connector vendors were very proudly showing 600 pin connectors, which is amazing that they're putting on a lot of pins. But even with that number of pins, the bandwidth that you get across an electronic pin is nowhere near what you can put on an optical fiber. So optics has been recognized for some time as the way to go for getting the information out of a processor chip.
One question.
Yeah.
So I think there's a wrong assumption that when everything's in the cloud, or it's just all virtual in the cloud. You kind of speak to what type of power you need for massive scale cloud operations, like the software service platforms that we're accustomed to work.
Right, so the question was, we think that the cloud kind of magically solves all problems. And it does a lot, but if you go to the cloud workstations, you'll see that they have a lot of memory stations. They don't have so much in processors, but they have memory banks. And you know, true, there's an incredible amount of data in those memory banks, but they are constantly coming up against the limits as the cloud usage grows. They're coming up against the limits of how can they get the information out of those memory banks fast enough, and how can they have enough memory banks and be able to route data to in and out of them fast enough to address the needs of their cloud users. So again, in these data centers, they're coming up with optical solutions for interconnecting their memory banks. All right, next slide. Let's go back. Actually, I'm sorry, I forgot to mention one thing. All right, what we're seeing is two views here. This is a top view and a side view. So in the top view, you have your wavelength separated out by the spectrometer. In the bottom view, you have multiple layers, M layers, and we had the number of 100 there. And what happens is that in each of those layers, you have this function. You have the wavelength division demultiplexing. So the demultiplexing gives you 160 individual wavelengths. And if you have 100 layers, then you have, I think it's 16,000 individual wavelengths that you're achieving. So you get through the inherent functionality of a lens will image a spot that originates in one point onto another point. And so you can get 100 separate points of imaging just through the lens. And then because the top view is spreading the light into the wavelengths, you get an array of 100 as seen in the side view, multiplied by 160 as seen in the top view. Next slide. Okay, now, an important thing that we want to do is to get the data that is inside the chip. Okay, first of all, where's the chip? The chip is to the right of the blue box on the left, and it's above the blue box on the bottom. So the chip is over in the space to the upper right. So there's data originating at different points inside that chip. We want to get it out, and we don't want to try to get everything out through pins. You know, we can't put enough pins on the side of a chip to get all of the data that's in there out. So we want to get it, we want to acquire the data inside the chip. So in order to do that, we take the waveguides that started with the spectrometer in the previous slide, and we run the waveguide into a modulator, Mach-Zehnder modulator. Now the modulation function starts with the data. The data is presented to a driver that amplifies the signal. Signal is split, part goes to an inverter and part goes straight. And the two parts are opposite each other, which doubles the effectiveness of the modulation. A Mach-Zehnder works by changing the phase, delaying the phase according to the voltage that's applied. So in one case, you delay the voltage, in the other, you retard it. So when you've done that, you create an interference between the two converging beams, and you get modulation. You get a choice between a 0 or a 1 on the waveguide. So these modulators are placed at different points internal to the chip. Putting the signal generation inside the chip has important advantages. It makes the high frequency RF lines inside the chip short, and that helps with bandwidth, crosstalk, and thermal load. It minimizes the volume occupied by the modulators. Our goal is 1 cubic millimeter per modulator, or 16,000 or more modulators in a chip, inside that chip. Next slide. Now here we're drilling down to what the modulator is. You saw that in small in the previous slide, but here we look at what's happening. You have data that's inside the chip. It's delivered to an RF driver that amplifies it. That signal is split. Part goes to an inverter, part goes straight. And those two RF lines that are adjacent to waveguides, and they cause a phase change in the wave that's in there. The optical wave originated from the spectrometer. The way Mach-Zehnder works is you split the optical wave, part is retarded, part is advanced, and you get the two branches out of phase, and you can get signal modulation. The signal can be allowed to come through strong, or it can be made to zero. Zeros and ones on the optical signal. So that's what I said here. Okay, next slide. Here's a detail on the spectrometer. You remember that the spectrometer was what happened when we came out of the frequency comb generator, and the wavelengths were all combined in one wave. So we have to split those wavelengths out. And the way it's done in this example is a grating. A grating will spread the different wavelengths into different points on the output. This particular spectrometer is a monolithic solid, and we choose that idea for robustness. You want it to be something that doesn't change its properties with temperature or vibration. So having an all solid state spectrometer is a good thing. And we're using the green is chalcogenide glass with a high refractive index, and the white is a low refractive index material such as calcium fluoride or silicon dioxide, fused silica. The grating itself is glazed. It has these little triangular features. The pitch here is about 10 microns between one facet to the next. And so these will separate the wavelengths from the frequency comb. And using the blaze gives you high first order efficiency. And we plan to have an index matching epoxy at the interface between the grating and an adjacent low refractive index material. Next slide. We expect I'll be giving you a quiz on how this spectrometer works.
In terms of the cost of that, have a little bit.
Yes, the cost of just for the spectrometer, cost is probably not a driver for our application, because the function is something that can't be done any other way, if you will. It has to be done by some photonic method. And all of the photonic methods that have been proposed generally tend to be expensive. They had a saying that in the old days the money was in the fiber, and now the bucks are in the mucks. So you can expect that the system will be expensive, and it pays for itself, however, because of the incredible throughput that you get. And on a per bit basis, it might be pennies. But the system might cost on the order of $10,000 at maturity, including spectrometer and the cones and everything else. Yeah. Okay, so how do we deploy this capability? And typically it will be used in a network of some form. And this is an example of one kind of network. It's hub and spoke. And optical broadband channels provide simultaneous bidirectional non-blocking broadband interconnection from the hub to all of the spokes. And however, spoke to spoke information transfer is only via the hub. You have to go into the hub and then back out. So a hub and spoke is a good concept. It addresses all of those spokes, but it's limited and it has to come through the hub. Next slide. Mesh network is a bit more capable. You have optical fibers, bidirectional optical fibers connecting each node to every other node. So number 1 connects to number 2, connects to number 3, and it connects to number 4. Likewise, number 2 connects to 1, 3, and 4. Every node connects to every other node in a mesh network. So the mesh topology provides the maximum input-output data transfer rate among cooperating processors. Next slide. Okay, so with these tools and you know, with the optical interconnect getting the information out of the processors, and with the different kinds of networks, we're going to build up a multi-stage expansion. We're going to build up a larger assembly of many processors. And let's start here at the blue dot on the bottom. That is a mesh interconnect hub, and it has around the mesh center, it has spokes. So it's a combination of the two kinds of network, if you will, but it connects to the system, or connects to this ensemble, starting out in the Y direction, where the hub connects direct spokes to a line of 100 processor nodes along the Y-axis. And then each of these nodes along the Y-axis directs a spoke to 100 processors along the X-axis. So now you have 10,000 processors, intermediate nodes in the Z equals 0 plane. So every node in the Z equals 0 plane now can connect to 100 processors directly above and parallel to the Z-axis. So the total broadband connected processor count in an XYZ volume is 1 million. Now, that is based on the example of 100 spokes. Our system that we looked at before had 160 maximum possible spokes. So that means that if you go to 160 instead of 40 is what that example I should have used. You get up, anyway, you get up from 1 million, you get up to 64 million processors that could be reached. So this system is very large. I hesitate to say that no one will ever want a larger system, because we have examples in history where people have said nobody's going to want more than such and such in the computers, and sure enough, 10 years later, they needed 10 times that much. But this is a very large system, and we also will have to say that you don't start out on day one with the maximum of 64 million processors. You start out, first of all, with proof of concept, And then you build up to that, and you're able to scale as much as you need to in the future. Yeah.
So earlier this week, AWS announced that they're building like the world's largest supercomputer. So to train AI models. So for context, like how big is that compared to what you're showing?
Well, I know about the fusions and the frontier system at Oak Ridge, which is 9 million processors. So, and there are two things to say about that. The number of processors that you have in your system is very important to what your artificial intelligence capability is going to be. But in addition to just having a lot of processors, you also want to have a very flexible way of being able to communicate among the different processors. So this system has the ability to structure the hardware, the optical fiber lines, in a way that would allow you to connect any node in this $64 million volume to any other one. The baseline method of connecting from an arbitrary point to a different arbitrary point would be to communicate back to the z=0 plane, and from there back to the x=0 line, and from there back to the hub, at which point your data would be routed through the hub back out to the other processor. And something to be aware of is that a processor chip has the ability to put data on any one of its internal I/O points through software. So what that means is you have a fully software implemented switching system that can connect any processor to any other with 25 gigabit per second data flow. And that kind of pervasive connectivity is what's needed, in addition to just the bulk number of processors that you have running in order to get true artificial intelligence. And just to elaborate on that point, the software for artificial intelligence typically will run with parallel processing. You'll have a mathematical problem, and it'll be parceled out to in pieces to a whole bunch of slave processors, and each of them will report back their part of the solution, and that'll be integrated into a final solution. Well, having parallel computation and going back to a core to round it out to finally get the result is a time-consuming process aspect of the situation. So having an ability to rapidly communicate between arbitrary nodes located arbitrary positions within a computation volume opens up different architectures that are not constrained to flow back through a center point, but that can be parallel, but also fully integrated. Next slide. So what is the relevance of all of this technology to artificial intelligence? Massive interconnect throughput overcomes bottlenecks in the present day state of the art. Presently, the data generated in a chip far exceeds the I/O capacity. And furthermore, thermal overload results from densely packed circuitry. And the system architecture is constrained by the interconnect limitations, as I've been saying. So the 4S solution guides CW continuous wave optical waves into chip interior, having the modulation occur at the chip interior does several things. It makes the high frequency RF lines inside the chip short, minimizes the volume occupied by the modulators. Our goal is cubic millimeter, 16,000 modulators in the chip, And blending mesh and hub spoke network configurations provide system configurations that support massive parallel processing and instantaneous network reconfiguration. Machine learning and neural network software makes effective use of groundbreaking infrastructure advances to close the loop in a path to strong artificial intelligence. Next slide. So this is, after all, a project program management organization. We should ask ourselves, what is the business development path for this technology? So first thing we want to do is to describe it. That's what the charts that you've seen here do. File a provisional patent, we did. And the next step in our path was to engage with the Department of Commerce. They have a Chips for America program. And under that program, we joined the Mid-Atlantic Semiconductor Hub, MASH. And in their response to the CHIPS manufacturing notice of funding opportunity for digital twin structure. And having done that, we made a lot of introductions, and this is an important subtext here, is that you have to find some way to get to know the community that you're going to be working with. And this Mid-Atlantic Semiconductor Hub was an excellent way, because everybody in that group was a subject matter expert, and these are the people that we need to work with to realize our design. So in parallel then with the Mid-Atlantic Semiconductor Hub and the Chips for America program, we initiate a parallel Department of Defense proposal leveraging 4S's Super 8A status. A Super 8A means that you are able to get a Department of Defense grant for up to $100 million without contest. You don't have to go through the RFP and response and competing and so on. You can go direct. What you do have to do is to find a program manager inside DoD who has the money and wants your technology. Okay, so based on our acquaintances at the Semiconductor Hub, we want to form a proposal team comprising these MASH participants. And we also enlisted the Naval Research Lab as a technology advisor and advocate within DoD. And that we got into just by accepting their invitation to a open house that Naval Research Lab was having, and showing interest in their work. So they were eager actually to help us out there. And ultimately, we want to spin up a photonic chip fabrication facility specializing in photonic interconnects. Next slide. The process is in 3 stages. You have to articulate the vision, organize pilot projects, and make a transition to industrial scale. This takes many years, but these are the steps along the way as they are planned. Now, let's go. Yeah.
Was it difficult to find a pilot project, because what you're really trying to prove is that it can support large scale solutions. But with a proof of concept prototype is only going to be a small solution. So was there risk there that the prototype may or may not work for a larger scale?
That is a distinct risk. It's not very difficult to come up with a pilot project. You just leverage that off of the technology. What does it do? And you just say, okay, this technology would be able to shoot 100 optical fibers with so many gigabits or terabits of data. But let's just start with 2 layers so that we can prove the idea that multiple layers are possible. And instead of 160 wavelengths, let's go with 20. So scaling it down to a manageable proof of concept size is not hard, but relating the scaled down version to an actual application could be tricky. You have, uh, actually, there are projects going on today where people do not have the need for extremely high data exchange rates. They might be looking for 100 terabits or so, and 20 wavelengths at 40, 25 gigabit per wavelength. It might be very suitable for certain applications, point-to-point information exchange. And one example of that is free space optical from satellite to satellite in low Earth orbit communications like Starlink. Next slide. Okay, we've told you what the orderly plan is. Here's what actually happens. Yeah, you have, you climb up. This is snakes and ladders. Yeah, you climb up for a while, and then the ladder breaks, and boom, you're back to ground zero. So yeah, we've had our share of that, and you just start over again and make it work. Next slide. Present day status, leveraging our Super 8A status to obtain DoD funding is work in process. Timeline is we have until May of 2024 to get traction with the program. May is the date chosen because that's when we have to file our full up patent, which is a transition from a provisional patent that we have now. You get 1 year after the provisional to file a full up patent. And so that brings me to a point where, yes.
How does the encryption and authentication of the data technology move with this?
Right. Okay. So encryption and so on is implemented through software, and the software resides on the processors. So the chip, you have to start with the chip, and in the software that organizes the actions of the chip, you have to have it such that the encryption is embedded in the signals at that point, right at the point of modulation.
So that's possible. That's not an issue.
No, that is done in the traditional way, if you will. That's a legacy capability. I should mention, by the way, that all of this technology that you see tonight is built on the shoulders of pre-existing technology. And the idea of optical interconnects is known, and there are people who are doing that work. And what 4S is offering is a multiplier, if you will, an enhancement that dramatically improves the capability of optical systems per se. I want more questions. I'm supposed to be up here for 40 minutes, so I need your help. Yeah.
Timeline sitting here until May of 2024.
Yeah. Oh, getting traction. So there's a bit of traction. We took the people who were in the Mid-Atlantic Semiconductor Hub and sent out our charts that you've seen here to actually everybody, and a fair number of them came back. So among those who came back, there were two houses. There was one that provides a digital twin software, and there was another one that is a system integration house, which is a very good combination because the system integration people know how to drive the digital twin software. So we're anticipating that we're going to be able to design our entire system in a digital twin environment. So I don't know if that answers your question. We got our leads for from being in the MASH program. Okay, we can go on to yeah.
Department of Energy, become a microelectronics program
Okay, DOE, this is the responder there. It says that DOE has a program that could be of interest, or they might be interested in this technology. If you come up after the session, we can talk some more. Yeah. Well, let's go on to the next slide. I don't, if a question is kind of bubbling up to the surface, please let it bubble and you can ask it at any time. Next slide. Now, okay, so I mentioned that what we're offering is built on pre-existing technology. And these references are written by people who are deeply engaged in that technology. And I understand that the charts will be available to people who attended the meeting tonight. They will be available, so you can get them. And then if you want to drill down into the technology, read these references. They're very good work. Next slide. And you can contact Bill Ziegler. He's the guy who can put you in touch with all of this. He's my boss at 4S.
So now we're going to introduce Mr. Ziegler for a fireside chat and bring this back down to a little bit more of what you guys can take away from this. So give us 1 second to set up.
Next investment, wireless mics.
Well, I would say it's an order of magnitude. The thermal problem is really big. So if you reduce your thermal load,
Whoa, now it's on.
so I don't think I'm live. Hello? Okay. So if you reduce your thermal load, you've done a lot to reduce the energy consumption overall. And furthermore, the RF lines in the conventional system where you are sending your information out to a copper pin have to be driven at a lot higher voltage than what we need for modulation internal to the chip. And it's a shorter run. So I'm just thinking broadly overall about an order of magnitude cost reduction. Bitcoin mining. Oh yeah, that's, I love Bitcoin mining. I own Bitcoin, I guess. That's the knock on Bitcoin, is it's very energy intensive. So different systems that would reduce the energy consumption for processing would bring Bitcoin back into the noble realm.
You have to push the button to talk.
Over here.
Oh, you have to push that to talk.
Yes, ma'am.
Over here. Is this a capability that can be added to existing chips with software? Is this software that has to be built into the chip? In other words, does it have to be, chip needs to be created?
The type of chip that we're talking about here that has optical modulators internal is all custom, all novel. We're talking about redesigning the processor chip to have this capability.
So at this point, you guys are looking for some potential funding and some potential production. Maybe industries that want this data center.
Correct. Yep, correct.
I did notice that, I think Michigan State, their science program are in the process of also looking at this capability. You know, MIT also does have, their science labs are looking to say, pass a competition. Competition, you know, not know of any.
I'm at a loss here, but well, the question was, do we know who our competition is? And just about everybody who does technology wants to get into artificial intelligence, so it's everywhere. But I think there was an earlier part of that question that I didn't pick up on.
Penn State.
Penn State
has a science lab. They're working on it. I think MIT is also.
Okay, yes, that's right. And look, Penn State, Columbia University was one of the references that I cited. And of course, it's international as well. And I think part of our motivation for moving quickly into artificial intelligence is that foreign nations are very active in it. And there are some very big prizes that will be awarded to the first successful development of strong AI.
The pathway for different nations is different than the US. So,
Correct. Yep. Penn State was the also the coordinator for the MASH project that we were. Probably have some MIT alumni.
Yeah, there's MIT is very active in artificial intelligence, and they were part of the Chips for America program, not through the Mid-Atlantic, but through other hubs that, in fact, were more. MIT was a member of a hub that was successful in getting a digital twins grant.
Unlike Penn State.
Okay, so just a few questions. So IT gets stale quick. What advice would you give for quantum computing projects to make sure, I mean, this can take years, but by the time it's ready to launch and be of use, it could be out of date. We see Amazon leading the field with this largest supercomputer in the history of the world. What advice would you have to make sure that you're not doing too much that takes too long that makes you behind the power curve by the time you release?
Very good question. A couple of answers relate to that. One is just move as fast as you can. But another one is to say that infrastructure has a life cycle which is more extended than software. You'll get a new killer app in software 3 months after the original idea comes out. But infrastructure means you're actually putting hardware on the ground, and that kind of a project has a longer life cycle.
The other side of that is, you know, those of us working in this field need to keep up with the papers and whatever everybody else is doing. So keep monitoring where we are so we can stay ahead of them or at least keep up with them.
Next question would be, what advice would you have for project managers, program managers who are looking to pivot into this field? You guys still have the majority of your careers ahead of you, but
We're just starting out.
Yep. But either people who are at the midpoint of their careers that are looking that, hey, maybe I was a programmer, project manager, that's a dying art. Like to be on that cutting edge, to be on the back end of AI, maybe not the front end so much, but the back end, what guidance would you give there?
Well, stay up, like the last question, stay up on the literature. Read all the literature that's out there on this. Surround yourself with qualified SMEs and employees that are also actively looking for. So if you're trying to build a team of the local or as many experts as you can find in that field. Don't just go hire some mathematician from Berkeley because he probably won't know anything. Sorry, that's an inside joke. But the biggest thing is to stay in the loop. Don't just bury yourself in the lab and follow what you're doing, but you got to stay in the loop and see what's going on outside, see what's coming down the pike. There may be things that other people do that actually contribute to what you're trying to do and help you build on it faster. Yes.
What advice to young people right now trying to pursue a career? What I for the computer science schooling with the advancement of AI, heavy AI use I use in the database in my job. Yeah, even with the need for writing scripts and things and what. So if given the time back for personal use. So what advice would you give the young people pursuing career in college that will tell me that in 5, 10 years, not 10 years from now, become obsolete, that AI will take one of those jobs. So what advice would you give to people right now as to pursue a career path in artificial intelligence or the traditional coding and computer science that would be out of our experience?
Ron, I'll let you answer this since you have 2 kids in college.
That question comes close to home. I have a son who's a sophomore at the University of Maryland, and he recently made a change in his curriculum. He was in computer science, and he changed it to computer engineering. Now, the difference there is that computer engineering considers hardware, and you have to know physics, chemistry. You take courses in physics, chemistry, and mathematics, a lot of math, and a double E as part of that computer engineering curriculum. So the advantage of having that broader hardware and software exposure is that you're able to pick up on the different threads that will emerge in the future and be able to work on those threads, whatever they may be, as opposed to purely software.
That answer your question?
Yeah.
Stress testing. Has the system been stress tested?
No.
No, this is all actually very conceptual. There's a lot of, the development work that will take place first of all, we think, in a digital twin environment, which is a simulation environment. And the simulation environment is able to do stress testing by postulating different environmental stresses. So that would be a first step. But of course, you're not done until you've done stress testing in hardware.
So it's not
No, this is ground zero. And there you go. That's a reason, by the way, to get into, for a young person to get into this field, the entire field is ground zero. There are laboratory experiments which do photonic interconnects to chips, but that's all just laboratory experiments. There are no developed systems at this time.
Okay, well, a round of applause for Mr. Smith and Mr. Ziegler. So they'll both be around if you have any questions. Santa Claus and Mrs. Claus will be at the Christmas tree for photo ops. Thanks to all who brought in presents for the Toys for Tots toy drive for Montgomery County, as well as last month for the food drive for Mana Food Center. So thank you. Yep. Yep. One program coming out of the new year will be our chapter scholarship program. So we'll have the application on the website. One scholarship is just for family members of chapter members. So it's a great opportunity to at least pay for a quarter of a class. But thank you for your membership. Wishing everyone a warm and safe holiday season, and we'll see everyone here back as a group in February. Thank you.